Hello, everyone. My name's Jared Longfox. I'm with the AIAA Space Resources Technical Committee, your host of the AIAA Space Resources webinar series. Today, I'm hosting Hunter Williams from Lockheed Martin Space. Hunter is an expert in oxygen and volatile ISRU and is now focusing on lunar power. From there, I'll let you take it away. So, without further ado, everybody, Hunter Williams.
Fantastic. Thank you, Jared. And yeah, I see a lot of familiar names in the participants list now. So really glad to see some of y'all. I believe that the you can put things into the chat or the Q&A. Is that right, Jared?
Yes, so sorry, I forgot to mention. Please punch stuff in the Q&A as we go. We'll get to I assume Hunter, you want to answer questions after your talk. There'll be
Yeah, that would be best for
yeah,
sure.
absolutely. So we'll have a Q&A session at the end. Punch them in. We'll get to them in order of entry.
Okay, fantastic. So yeah, like I said, I'm Hunter Williams. So I got my MS in space resources in 2019. I'm currently working on my PhD there as well at Colorado School of Mines. My topic area is in the lunar electrical grid. While I was at Mines, I did a number of different ISRU technology development efforts. I was a NSTRF, now it's called NSTGRO, NASA fellow working on uh, additive manufacturing using molten regolith that helped me transition into MRE work. And yeah, I also did some fun things with the last person to talk here, which was Joel Sercel on the Transastra optical mining system for asteroids. So I've had a lot of fun with ISRU in the last 10 years. Um, I was the business development manager at Honeybee Robotics from 2019 to 2023, and I am now working at Lockheed Martin as BD senior staff for lunar infrastructure. So my purview is basically everything that goes on the lunar surface that may be there for the long term. So we're going to talk about three different topics today: commodity production and a lunar economy, space resources, infrastructure, and power, how they relate together, and then what a lunar grid might look like. So the important disclaimer here is that you notice there is no Lockheed branding on this presentation. I am not representing Lockheed today, and these are not Lockheed's views, just my own. So first talking about commodity production. And I'm going to get a little bit into the details of what a commodity is, what an economy is. I think it's really important to define these things because so often when we're talking about commodities and a future lunar economy, what ends up happening is we end up thinking of like just people selling to other people, and that makes an economy. But really, it's a little deeper than that. And the truly important thing for people to think about is labor value. So if we go back to Adam Smith, um, I think that talking about where value comes from in commodities is really important. Commodities can be traded back and forth evenly. If you got 500 shoes and they're worth 100 jackets, you can trade those back and forth for each other. And the reason is that all the value inherently in a market that has many different traders is built around labor value. The labor uh, brings value to natural resources from extraction. A piece of gold that's in the ground that is not extracted is not actually worth anything. It's not until you have labor to get it out of the ground that it's worth something, which is why there are huge gold deposits in Alaska that are completely unmined because it's just simply too labor intensive to get the gold out of the ground. You have the multiplicative value factor of labor applied to machines, and then you have the direct labor itself. So when these three things combine, you get a commodity. So when we think about lunar commodities, we have to think of how these three things will combine. It's not just the natural resources. A lot of times we think about, like, I will verbally mention George Sowers many times in this presentation. You know, when George Sowers, one of the professors at Mines, was working on the uh, even before the commercial lunar propellant architecture, working on at ULA, getting a price point for buying propellant on the surface, a lot of people thought that the important thing there was just the cost of the raw material. But if you don't factor in the cost of shipping the machines up to get it and the cost of the labor to produce it, the very expensive labor when it comes to space, then you can't figure out which thing you need to reduce the cost of in order to um, enter the market. Because when you're trading a commodity, especially in the same place, you have to be able to come in at a price point that is lower than the competitors based on reducing the cost of one of those three areas that make up the value of the commodity. So, what would a lunar economy look like? There's a lot of talk right now about lunar economy. One of the really important things here is that it's not just about having commodities; it's also about the directionality of money, right? So if you have something where money is only flowing in one direction, that's not an economy, right? So if we look at mercantilism and colonialism, the only way that those things were supported, as in the only way that those financial systems were, able to not collapse under their own weight, was through violence. So since that's not what we're doing on the moon, we we simply will not be able to maintain a lunar economy until there are commodities that are being produced on the surface that have an equivalent value to something that was brought from Earth, and that can be easily swapped back and forth. So where some of the value is being produced on the surface, as long as you have the majority of labor and the cost being labor, the majority of those costs through labor, bringing that money from the surface, then eventually you run out of money on the surface. So just having a few trades is not enough. You have to have something where there is a completed circle of trades. And if all the money is originating at NASA and then going to contractors, and then it's just contractors paying each other, you can trace that money back to NASA. It's vitally important to understand that the source of the money, even if you have two independent groups who are not NASA trading back and forth with each other, if both of them were originally paid from NASA and all of that money is eventually getting used up as the use value of the commodity is the part that's important, then it disappears. So let's talk about a real independent lunar economy and what that timeline might look like. Again, this is just my opinion, not Lockheed's opinion. So right now, all funding really comes from NASA. We have some token things from other groups. We have some business to business type things, but most of them are just there to kind of get the legality of doing trades on paper. There's no real lunar economy. And part of the reason that there's no real lunar economy is that there's no lunar infrastructure. There's nothing there to extract resources from the ground. There's no labor going into the moon. All the labor is done on Earth and then shipped to the moon. So, what about 10 years from now, right? Most money is still coming from NASA. Maybe there will be some from foreign governments. Maybe there will be some with the DoD. Who knows? Um, Here's where things get interesting. NASA starts to test ISRU in human systems, or I mean, really in any capacity. But once NASA can start to use propellant in its missions and can start to depend on infrastructure that was not brought from Earth within that same mission, then that changes a paradigm exclusively in the area of ISRU use and infrastructure growth. That does not yet create an economy. So you will see some real business to business sales here, but for the most part, the funds will still be traceable to NASA. Now, once all of that infrastructure is in place, especially once a power grid is in place, then there will be commodity production. Commodities require stable infrastructure. Again, using the example of gold mining, very few gold mining operations are such where you fly out, mine the gold, bring all the gold out, and bring all the equipment out as well. The mining operation needs to keep its infrastructure on site, and perhaps you are flying people in, or maybe even you're robotically operating at the mine site, and you're bringing out as much refined material as possible. But if the machines aren't staying there and being used, you don't have a mine site. So some of the customers for commercially sourced ISRU commodities would be, like has been previously stated, things like LEO satellite refueling using lunar propellant, or oxidizer, as the case may be. Perhaps using lunar and asteroid source materials to make big construction projects in space, like mega satellites or future habitats, things like that. These are things we can speculate about, But the really important thing is you can only disrupt an economy when you're providing something that is really needful, right? If you can only vaguely prove the use case, you don't have a commodity yet. So I think it's going to be a couple of decades before we get there. But ISRU can be brought into the value chain early, and infrastructure can start getting in place in preparation for this. So one of the things I keep reminding people is if you really want to see a commercial lunar economy, keep pressing NASA to get real infrastructure on the surface. This whole idea of transition to industry, I think we should throw away. There is no transition to industry until there is infrastructure on the surface. So here's how a little bit of a cheeky way to think about ISRU and commodity production. Okay. So first, decide if you want to do science projects or if you want to actually build infrastructure to make commodities. Going up and producing a couple of little poofs of of oxygen is not ISRU. ISRU, like breaking it down, in situ resource utilization. The utilization is just as important as the in situ. You have to make something useful. And to make something useful, you have to make something where you can have a supply chain where it is a recurringly useful thing. If it's only useful one time, then it's not really a commodity. So once you understand that you want to build infrastructure, determine where value comes from. Okay, what part of the three-legged stool of value of labor, natural resources, and machines are you going to make cheaper so that you can compete with terrestrial produced products? Any efficiency in any one of those categories, if you are truly bringing down the price, is what is going to lead to market capture. If you're not bringing down the price, you're not getting market capture. Even if NASA is funding the technology development, and that's a really important thing, I think, where even if it's cool, even if it's you know got the NRE bought down through taxpayer money, unless you're producing at a lower price than can be produced from Earth, then risk classification alone is going to knock you out of being able to sell commodities. Step 3, and this is where we get to kind of the title of my talk, determine what's needed to provide an equivalent value on an existing commodity anywhere in space, lowering the cost by using ISRU. And I think the only two ways to do that in the near term are through cheap transportation and permanent power. There are some groups that have got cheap transportation in their crosshairs. They are really working hard at it, and I applaud their vision and their efforts. For the rest of us who cannot pay for multi-billion-dollar rocket development, permanent power is probably the easiest way and cheapest way, most immediate way for us to enter the value chain, simultaneously being as important as cheap transportation. So let's talk about what this looks like, the relationship between space resources and power. So first, talking infrastructure in general. You have to set up infrastructure in order to produce commodities. So power is, I think, the most important one, not just generation, but distribution and control as well. So there are a lot of people talking about generation. Generation is very important. VSAT, FSP. We even have space-based solar power and a few other heterodox ways of producing energy. But I think distribution and control are going to be very important parts, perhaps even more difficult to build properly than the generation systems, because the the risk tolerance for space missions is vastly lower even than that of Earth, right? If your power gets knocked out on Earth, you can stay alive for a couple of weeks. I mean, especially if you got water still running, you can stay alive for months. I was in Hurricane Ivan in Florida, and we didn't have power for like 2 months, right? We kept getting water deliveries from the Army Corps of Engineers. So yeah, we survived. In space, you got hours tops. So having a grid that can do proper load shedding whenever the load and the power generation from one utility are mismatched, having a grid that can do fault management, that has human in the loop control, so that you can determine when the machine's going haywire and needs a little bit of the human touch, but in general can react faster than a human can, so that it's not just one guy pulling a bunch of switches. that is extremely complicated. We've never done it in space. We have the ISS, which is about as close as we've ever come, but even the ISS does not have the kind of power requirements and fault tolerance that will be necessary for the lunar surface, because the ISS has pretty rapid resupply possible. With the moon, it takes at least a week to get things set up to ship up to the moon. So you have to have everything there 100% of the time. But beyond that, there are many other parts of infrastructure that will set up this value chain. So propellant production and storage, ISRU manufacturing, surface mobility, transportation, meaning launch and landing. And yeah, it's part of a larger ecosystem. I think the power comes first because the power is what enables every other surface asset. So how good does the infrastructure actually have to be to start creating value? If I can uh, sell you a McDonald's hamburger and somebody else is trying to sell Ruth's Chris Steakhouse steak, right? Then both of us have fed you, should be okay, right? There are certain scenarios in which a McDonald's hamburger is more than enough, and there are certain scenarios where what you really need is a salad. And so I think what we want to talk about is um, how quality matters and how price point alone is not enough to consider. You have to consider price versus value. So risk classification, I think, is one of the most rapid ways for us to start thinking about this price versus value concept, because NASA is already kind of putting things in those terms, just not for salable commodities. Risk classification is really price versus value when it comes to meeting mission requirements, but it can easily be adapted to start thinking about price versus value for commodities production infrastructure. So where is the risk being tolerated? Is it being tolerated by the producer, as in they are taking on all the different risks, buying them down, setting up the system such that there is extremely low risk on the consumer? Or is the risk being tolerated on the consumer side, where maybe you will, maybe you won't get your commodities within a certain time frame? Maybe you'll have everything shut down. Maybe it'll be long-term stable. Hard to say, right? That is the difference between Class A and a Class D or subclass D mission. So it also is the difference in cost. So that extremely high class, low tolerated risk system is going to cost way more, like double or something, what the extremely inexpensive system is going to cost. I forget the exact numbers, but in documentation alone for Class A missions, you're looking at a very large percentage of the cost. Human missions are Class A. A lot of technology demonstration missions nowadays through STMD are Class D or subclass D. I think that we, when it comes to infrastructure development, should be doing things such that the risk is bought down on the infrastructure side. Why? Because that means when it's already bought down, especially when NASA is funding the infrastructure production, then the commodities can be cheaper on the other side. But most importantly, they can be reliable. You will actually have a value chain. Anytime if you need gas in your car, but you can only buy gas every 500 miles, it makes it very difficult for you to buy that kind of car. That's why electric cars were not very popular for a long time, because people had to plan the routes. A lot of people had this perspective that they could only stay in their city, right? So it is also a part of value is how stable your supply is. Um, and we're going to talk specifically about how this relates to the lunar grid, because if the core of the grid is Class A, if your control structures and your sensor system is Class A, then your other systems can be a lower class. But if your control structure and your sensors are lower class, then everything is automatically low class, even if it could be high class by itself. So let's talk through risk and specific ISRU commodities. So when we're talking about, for example, water ISRU, the commodity for satellites, the commodity is either water or high test peroxide, oxygen, hydrogen. There's a lot of different potential products that come out of a water ISRU value chain. I talk about the required infrastructure challenges and risks separately because I think challenges and risk classification are not the same thing. You could have a lot of different challenges that could represent financial risks for such a system, but when you're talking about risk, what you really should be talking about is propensity for mission failure. And single point failures really plague ISRU systems, particularly water ISRU. So looking at oxygen, so like something like carbothermal. So some of the challenges are the same. Like there's not yet a market for it, right? But also the TRL drives the risk. So something that has a lot of uncertainty with the ability for the technology to function at all should, by definition, have a much higher risk classification. Um, that's remediable, and I'll put these up and just kind of talk in a larger sense. Um, Specifically jumping down to power because I've already talked about some different ISRU like other like physical solid commodity productions. But when it comes to power, a lot of times we don't think of that as a kind of ISRU unless you've taken Dr. Dreyer's classes, in which case you know that there's a lot of different things that are resources. Uh, Power is certainly a resource. So um, the biggest challenge is that ESDMD, Artemis mission planners, have not yet planned for commodity use of power in space. But if we could knock out that challenge, if we could convince ESDMD to actually use it either as power augmentation, you know, like backup emergency power, or to start integrating it into Artemis, that could be our first commodity. The true risk is to utility. If you only have a system that is subclass D, it can only work on very experimental systems, low cost systems, and it cannot touch human system. You've limited your market. So as a commodity, even if you could sell to the human market, which is going to be the largest market, because your risk classification doesn't match up with the needs of that market, you actually can't sell that as an equivalent commodity to what's coming out of primary batteries. If you had a high class system that had the same reliability as primary batteries, once you get enough infrastructure in place, you can make it cheaper than primary batteries because you are getting rid of the launch cost of the mass of the batteries, which is, you know, especially for something that requires in the tens of kilowatts for something like a HAB mission or any kind of long-term lunar surface mission, that cost of mass for primary batteries really gets high. So the power system is enabling all of these other systems, but it's also enabling NASA to drastically lower costs of existing missions. So yeah, let's talk about permanent lunar power, my favorite type of ISRU. So night survival is probably the most relevant aspect of all ISRU systems, of how power helps all other ISRU systems. If you cannot survive one night, you're not doing ISRU. You do not have a space resource. You have a science project. Being able to survive for multiple nights, especially getting into multiple years, is the core missing requirement for most of our ISRU designs. I think if you look at the Moon to Mars architecture, it's not in the Moon to Mars architecture. It's spelled out for some of these things in the objectives, but if you get down to the functions, it's missing. So I think as a group, as a community, when we talk about ISRU, we should be talking about the requirements of permanent power because we don't have anything until we have that. Full-time operation obviously is very important. You don't want to just operate a couple of hours a day or a couple of times a month whenever you get your resupply of primary batteries. Surface power is also both available and commodifiable. So figuring out how your product could be commodified is a extremely important part of ISRU. So for example, when we think about metal production on the surface, figuring out what what it's going to cost to get that metal to somewhere, but also what that metal is going to be used for and how it relates to something from Earth. So, in this example, like let's say we were doing metal production on the South Pole, producing aluminum. How does our aluminum compare to 6061 or 7075, whatever it is that's being shipped up for use from Earth in the HABs? How does our aluminum compare for purity? How does it compare for cost, of course, but how about for testing? Like not just does it have the right purity, are we able to test the purity on site on the moon, right? So if you have all of this bulk material that is possibly way cheaper, possibly of the same quality, but you just can't test it, then you don't actually have a commodity. You're missing the thing that makes it equivalent on the market. Power is interesting because power is power. Once you have specified um, your power quality, you know the amount of voltage fluctuation that your system can take, the watts that you're putting out, and you have systems in place for testing that. So you have sensors. You're good to go. Uh, Sensors for power quality are fairly straightforward. Sensors for oxygen quality or metal quality, especially if you need to get statistical analyses of lots of, as in like not a lot of, but lots as a unit of your produced metal. This is true infrastructure, right? It's not something that you can ship up very easily from Earth. So that is another point in favor for power. But what's interesting is, let's say we do want to do oxygen production, right? So the closer you get to creating a commodity that is exactly the same as the cryogenic stored oxygen from Earth, the more power you need. So just producing oxygen in the beginning, like let's say we use the carbothermal example in the previous slide. So you've sucked off some of the oxygen from the regolith. Great. How do you know it doesn't have contaminants that are going to immediately cause your system to blow up? Like there's uh, a cryogenic liquefaction system is in there, of course, but even before you get there, you have valves, you have sensitive electronics, and from my own personal experience, when you have something that is extremely hot, that is producing molten droplets of gas or molten droplets of glass that have been gasified and carried through the system, then you are, yeah, you are possibly um, going to go through a lot of uh, things that are not consumable that will get treated as consumables, elements of your system that will have to be replaced because of this, but also exponentially the power requirements get higher the more you are testing and preparing your materials. So we should factor in the cost of power when we are factoring in the cost of our ISRU. So another really interesting part of this is that surface mobility and straight space transportation systems are large, expensive, and low in modularity. They are holistic systems. What that means is if you're a small business, maybe you can get subcontracted to SpaceX or something. But generally speaking, SpaceX is building top to bottom their rocket, right? But if you're talking about a power system, then there's a lot of basis for modularity within the power system because as we can see from our power system on Earth, right? Like any old contractor can go to the hardware store and buy replacement switches to put into your house. There are teams of different crews that can go and do repair operations on power lines and on transformers. It is not one global utility that provides all that, right? So it's very interesting because we have a multi-company supply chain for power on Earth. We don't really have that kind of supply chain for a lot of other potential ISRU systems. Certainly with something like water, you could have maybe one or more purification system, one or more storage system, something like that, one or more excavation system. But generally speaking, there's only like 5 or 6 places in that value chain. In power, you can plug and play very quickly. So I think that power is its own type of very interesting um, democratizing force, both for end users, but also for people who want to play in the space. So now I'd like to talk to you a little bit about what a lunar grid would even look like. And this is a bit of a change of pace from the rest of the presentation. So uh, stick with me. I think this is the fun part. What is an electrical grid? This is a question that I think we should always be discussing when we're talking about um, power ISRU, because what parts make up the grid on Earth will have to be uh, translated in some way to the moon, right? So we can't just ship up the power system and say, this is my grid, this is it. So let's talk through what this is, and then we'll think through how that could be translated to the moon. So with power generation, y'all are probably most familiar with that. On Earth, we have wind, solar, nuclear. We have oil and gas powered turbines. On the moon, we will likely have um, vertical solar arrays to start, fission surface power next, and then some of the other exotics after. Um, Immediately coming from the generation system, there could be substations right there for stepping up the voltage. So you can think of substations on either side of transmission. But transmission lines are the long lines that come away from the generation system. These are big, thick lines that lower the amount of power that's lost because they crank up the voltage. They allow the voltage to be cranked up very high to lower power losses. So after these long transmission lines with very high voltage, you get to substations that knock the voltage down for local distribution. So that could be distribution like in your area of the city, in your county, things like that. So the the distribution lines are much smaller, um, but much more convoluted than the transmission lines. So we have to think of transmission and distribution separately because um, they they will likely have very different form factor. I mean, certainly they do on Earth, but thinking about how it would happen on the moon is important too. Once we want to get beyond just the persistently lit regions, then immediately we need to start thinking about if we need a transmission system in addition to a distribution system. After the distribution system, the local networks of cables that you see when you look out your window, and the power lines, then you have your end users. And there's a point at which the power utility says, all right, after this, it's on y'all. It's on the customer. Your house is post demarcation point, the marked point at which the utility stops considering it their responsibility to fix things. So your house wiring is post demarcation point. The electronics that you use in your house are post demarcation point. Figuring out where the demarcation point will be on the moon is an interesting issue. Where should the utility have responsibility for keeping things from catching on fire? Is it at the individual payload level? Is it at the lander level? Is it at the distribution system that feeds the lander? What if the lander is part of the generation system and we have a massively distributed grid where every lander has a solar array on it? Well, these are really important questions, and those questions are most easily answered, I think, by having a high class control system because it can accommodate multiple concepts of operations, and you don't have to have as clear of a delineation between your end users and your distribution system. So beyond those major sections of the grid, the major hardware elements of the grid, you have the utility itself. So the group that is running the grid that has the software tracking all of the sensors, making decisions for problems, reporting on these problems, and then having larger planning sessions with the humans to either uh, increase the capacity, the infrastructure, or catch problems that the computer system didn't catch. You have a network of sensors and controllers spread all throughout the grid, and this is something that is oftentimes not mentioned because we, it's not that sexy to think about what sensors are you going to need to figure out if your little element is what's blowing out the rest of the grid. But we truly have to do that from the beginning, and we have to figure out how they are communicating. I'll get to that in a second. But if we have a wired grid versus a wireless grid, how smart your individual sensors have to be and how able to communicate they have to be with the utility is vastly different. So beyond that, we have transportation, so just getting the stuff in place, and then we have installation and repair. On the moon, installation and repair is extremely non-trivial. One interesting thing might be apocryphal, but it is attributed to Jeff Bezos, is that he said he has 1,000 robots in his Amazon market or his Amazon warehouses, and not a single robot can fix another robot. I don't know if he actually said that or not, but I love the quote because uh, we have to think about that on the moon. We will more than likely be trying to rely um, on robotic repair services, and they're simply not used very much on Earth. So anytime you have something where it's like um, a problem or an issue with the ISRU system has come up, and the solution is something that has never really been implemented on Earth, but that could be implemented on Earth, it's really important for that to be the pause to say, why? Why are we not doing that on Earth? In the case of repair robotics, it's because humans are actually extremely good at fine motor things. We're both strong enough to handle quite a bit of load, but we also are able to put very small things into other places. We're able to see better than a lot of computer vision can. So humans are great at repairs. Robots lag behind. We don't have many robots that have the kind of multiple capabilities that a human hand and eye does. So it's something that we really need to think about with our ISRU in general, but grid design in particular. So this is what a wired grid would look like. The sensors are connected to each individual element, and the mission control / utility is talking to those sensors, and through that talk and controllers, and through those sensors and controllers talking to the elements. So the interesting thing here is if there is a problem with any one element, because the system is wired, pretty much the entirety of the system knows immediately that there is a problem. The point of the sensors and controllers is to localize and isolate the problem, right? If we had a wireless grid, it's a very different scenario. So the laser, if like, let's say we were using a laser source pointed at a laser receiver, that laser source cannot know that there is a problem with the receiver. Let's say the receiver is completely burned out and it is not transmitting back data to the mission control saying it's burned out. If you don't have a laser source that is talking to mission control and saying there's no signal coming from the receiver, is down condition, stop sending power, that laser could continuously be sending power and just further burning out the receiver. So you have to have a very complicated system of both sensors and communications and software so that all of these things can talk to each other. A really interesting thing here is that the software it's there for getting the sensors to talk back to mission control, but it is nowhere near as complicated as in a wireless grid. So I'm a proponent of wireless grids. I think they're really interesting and they have their places, especially if you have very few elements and you have very long distances to cross. But the complexity of the individual element is much higher for a wireless grid. And then I'd like to talk a little bit about the comparison of each grid by class. So if you had that class A grid that I talked about before, semi-autonomous, highly tested, it's good to go out of the box, so to speak. It is able to confront a number of contingencies, and it is able to reduce downtime significantly. And that's really what we're going for at the end of the day is how do we keep downtime to as close to zero as possible so that we can actually support astronauts. You can also grow quite a bit with the Class A grid. So uh, there are issues like islanding, where you have a couple of power systems, you have loads between them, and the systems are not communicating properly with each other. So the load shedding software gets a little bit confused and one power system ends up trying to power the other power system. All right. This happens a lot with solar arrays, even on Earth. This was an issue with early introduction of solar arrays into the terrestrial grid. So what happens is you blow out everything in the line between the two power systems. So if you have a grid that can't recognize that that's happening and can't stop it, then the blowout happens and there's not any coming back from it. If you have a grid that can sense when power is going in the wrong direction or when there's voltage fluctuations that match up with certain down conditions, then the controller can stop them from sending power to each other, isolate them, figure out what's going on, send out repair teams or reboot the system, whatever it takes, right? But with the lower class system, you're going to struggle to do that. The only benefit to the lower class system is the cost. It's extremely low cost compared to the expensive system. But in the long run, when we were talking about commodity production, we were talking about infrastructure, startup cost versus eventual cost end up being similar between the Class A and the Class D system, but the value produced by one or the other is very different. And yeah, this kind of gets to what I was just talking about as far as like what is enabled by the Class A versus the Class D system. Basically, you get everything in a Class A system as well as the Class D system. But with the Class D system, you just get what's under the Class D heading. So in the Class A heading, you're talking about supplying power for billions of dollars in assets and leading humanity back to the moon and eventually to Mars. With the low cost system, you're talking about supporting like in the beginning, supporting like CLIP style missions and technology demonstrators. Eventually, you could get to the point of storing ISRU products. Now, this is an interesting thing. If NASA can depend on stored products, and they know that the stored products exist, there's no power required for keeping them stored, then you could have a functioning ISRU system even with a Class D grid. So things like bulk water, if they could find a way to, or high test peroxide, these kind of things that can be stored with very little oversight, they could be your first forays into ISRU systems that don't require this Class A grid. So I'm not saying it's impossible that commodities could be produced. They could. The only question is, how much of a just-in-time commodity producer are you? If you have to stockpile a lot of your commodities, that does lead to operating costs, but also the purchasing is done in bulk rather than at single point of sale. And that is an important thing because the modern economy is not based on buying things for years at a time, like the way that we do commodities in our economy now. It's based on buying things when you need them. And when you have a very lean economic system, the closer you can get to buying something right when you need it is what the market will tolerate because it requires less and less cash on hand. So another point in the Class A grid's favor is that in the long run, it will require less cash on hand for commodities. So recap of some major concepts, and then I think I'm going to come in right at that 15 minutes for questions mark, if not a little bit less. ISRU is based in commodities, meaning we are not just going and producing a puff. So, there are systems that are very interesting as far as like oxygen production, water production, but until they are semi-permanent or permanent, and they are producing at a volume that is relevant for use, then it's not ISRU. It is an interesting technology development, but it is not a space resource. Okay. Commodities have to have a trade value and a use value, even in space. You have to create value of an equivalent level of value at lesser cost in order to enter a market, which means, sure, maybe we can create new markets. Maybe we're going to be developing all at once an ISRU and power and infrastructure system, and all at one fell swoop, this thing will spring from Luna's head, like Artemis and Zeus. But I don't think that's how things are going to work. I think that it's much more likely for the first commodities sold to be equivalent to Earth commodities, but just at a lower price than how they're produced on Earth. Power infrastructure is the first things needed, and it will enable all other ISRU technologies. The most expensive option sometimes creates enough additional value that the value versus cost ratio skews in favor of the expensive items. And the grid is a classic example of this. I'm going to leave you with some thoughts, a vision of the future, commodities being produced throughout cislunar space, uh, water, oxygen, manufacturing, power beaming, the dream of a return to Earth type of resource is there. Um, we are at the point where there are multinational cities being built, springing up at both poles, and these emerging space nations like Portugal, Zimbabwe, are taking part in building up these grids and building up ISRU systems. Small businesses are doing it by themselves without the support of big governments, and yeah, a true lunar economy has started to exist. And finally, with all of the reduced risk and cost of missions by using ISRU, in particular power, then NASA is able to finally send people to Mars. That's my talk, and I'm going to open it up now for questions. Thank you so much.
Awesome. Thank you, Hunter. Great and informative talk. So first in the Q&A, there's a mention that if you go to AIAA's webinar site for today, this does not show up. Yes, I am actually currently working with AIAA to get this on their calendar. So thank you for the heads up, and I do apologize for that, everybody. You should see that up hopefully soon. Um, the next question states, I've been working on secondary battery storage using different technologies, batteries, reaction wheels, capacitors. Hunter, what is your view of using different technologies in the electric grid on the moon?
So I think if you have a core that is a high class grid that is able to separate the risk from experimental technologies and humans, then you can absolutely test these kind of things out. I think it's actually a very interesting concept to have um, things outside of just normal battery chemistries tested on the moon. Reaction wheels, capacitors, absolutely. So you just don't want these things discharging and shocking the humans to death. So, highly recommend uh, this kind of thinking, this kind of small, like truly small business thinking of how we can work together to build out something much larger than any one company could build by themselves.
Cool. Cool. Awesome. Thank you. Next comment says, excellent presentation, Hunter. Thank you. And I agree. I don't see anything else in the Q&A. So while I have a second, I'm going to take host's prerogative and ask, at the very beginning, or well, towards the beginning of your presentation, you mentioned that there can be no transfer to commercial before there's existing infrastructure. Can you expand on that a bit? I'd be curious to hear more of your thoughts.
Absolutely. One of the recurring themes that I have heard from NASA is that there is a transition to commercial that's going to happen, right? As in, commercial is going to be providing these services, and NASA is going to be one buyer among many for these services. That came out with LTVS. It's come out with some of the verbiage from the Envision Futures, right? So this is something that I think NASA as a whole, not just STMD, but NASA as a whole, is committed to. When we look at programs like SpaceX developing like for commercial crew, commercial cargo, right? A lot of times it's very interesting. Um, the the way that it is presented is as if SpaceX just paid for it all itself. That's not how it happened, right? SpaceX was paid to develop these rockets and then provide them as a service. So I think that that approach to NASA helping buy down the risk, buy down the NRE, the non-recurring engineering, and then transitioning to commercial as a service is really important. And we as a community should not let go of that. I understand that there is a place for, you know, uh, corporate contribution or what have you, but I think for multi-billion dollar infrastructure, the most important thing is to make sure it's going to work, to make sure that it has got the risk posture that NASA feels is appropriate for human use, because we want people to live on the moon permanently, not for a couple of weeks at a time. We don't want Artemis to be boots and flags missions. It is a order of magnitude more difficult to make something that will last for multiple years than what will last for a couple of weeks on the lunar surface. And I think we need to be starting from that perspective um, rather than saying, well, commercial will figure it out sometime.
Awesome. Thank you. A couple more did pop into the chat. So every time I travel, I need to bring multiple outlet converters to make sure my electronics can get local power. How does standardization of electrical systems play a role in the lunar power requirements?
Great question, Jarrett. So, uh, funny enough, I think the plug itself is the smallest problem. And I know that it's the most annoying problem here, but imagine if you had the same plug. You're back in 1880, okay? And you have the plug that is standardized for America, but you go from Boston to Atlanta, you plug your thing into the wall, and it fries it and it burns down the building, right? The power quality differences in early microgrids was pretty wild. Okay, so some grids were operating at different frequencies. There was a lot of non-standardization even among the basic electricity that was being produced, right? So nowadays, what's incredible is that across the globe we have more or less the same standards for power quality across all grids. So plugging in the correct plug into the wall is not going to fry out your system. Uh, the That being said, so I think that we need a standardization for sensors. We need standardization for power quality, and from that we will get standardization from standardization of the plugs, the outlets. So there is very little reason for different companies to want to develop their own plug and try to keep things proprietary if they have to have modularity when it comes to their voltage conversion and their sensors. So I think starting from the place that matters the most and trickling down to those other kinds of physical standards will be the way to go. But that's just my opinion. Other people, different opinion. Definitely not making that as a representative of Lockheed. Next question.
Awesome. Thanks. So, do you envision a Tesla versus Edison battle for lunar electrical standards?
Like a rap battle.
Yeah, kind of.
I, I. Oh, by the way, hey David, how you doing? Um, so I don't necessarily I don't see two separate types of grids forming. I understand the heart of this question, which is you have two kind of different approaches to the technology, and having one win out versus the other, especially like people talk about AC versus DC as like the classic Tesla versus Edison, which may happen on the moon as well. I don't really see that as an issue because I think um, one of two things happens: either somehow someone with a whole lot of money goes and pays for everything and makes it happen by themselves. Doubt, or NASA pays to build this infrastructure up. If NASA pays for it, then NASA will set the requirements. And so we will have the decision made on DC versus AC, things like that. And, people, I think it's very popular right now for like at conferences for this to be debated. So it makes it seem like it's more of a controversy than it is. But what it's really going to come down to is where the money's coming from and what those people who are controlling the money want. And once we have that core of the grid built, as far as like if it's an AC or a DC core grid, the requirements for the growth of the grid are what's going to drive the rest of it. So if we do end up needing to go, like if it starts out as a DC grid, DC microgrid, and then we end up needing to provide power from like for example, from an FSP system in a PSR out to multiple tens of kilometers away, well, AC starts to look pretty attractive then. But that is a very specific ConOps and mission scenario that we don't have defined yet. So thanks for the question, David. Thank you, Christian. Appreciate your compliments.
And
Uh,
yeah, Parker asked a question that I'm personally curious in as well. What is the role of academia in all of this?
that's a great question.
Yeah.
So, especially if you have a high reliability grid in the middle, right? What are like what was I doing in academia? What's Jared doing in academia? You know, developing these like really um, interesting technology, like cutting edge technologies that pretty high risk, still need a lot of NRE buy down to be ready for prime time with space flight, right? So I think academia continuing to push the edge when it comes, like push the envelope when it comes to technology development is going to be part of this until we have I mean, basically forever. You know, that's what academia does, and then industry takes it up and turns it into products. So, I think I think I would love if academia was continuing to push it, to poke at NASA, to say like, hey, we want to keep doing what we're doing. We don't want to turn into, you know, utilities. We don't want to be stuck on Earth. We want to be testing this stuff in space. So pay for the infrastructure to get this stuff tested in space. I think that's the way I think that's the voice we should be speaking with.
Awesome. How do you think international competition for prime power sites might play out?
Well, that's yeah, great power theory, right? It's an interesting question. Um, some of it I just don't know. I have opinions. You know, I lived in China for a while. I've lived in Japan for a while as well. Um, I will say that I think it is interesting that some of the identified sites that China is interested just happen to coincide with the Artemis selection sites. Um, I think I think that in the long term, we are going to uh, we're going to find that certain sites are just better than others for producing power, and also they may be the closest to some of the water deposits, right? So it is a limited resource that may drive certain aspects of competition. However, um, I don't think that I don't think this is necessarily something that we need to start pounding the alarm on right now. Uh, Mostly because I think NASA's just not funding to the like ESDMD is not working on this stuff just yet. You know, SMD I'm not sure if they're interested at all. I think we need an infrastructure mission directorate, possibly a new mission directorate specifically for this kind of stuff, whose job it is to make sure this happens. We have somewhat something like that if you think of the ISS's infrastructure, but the mission, I forget what its acronym is, the mission director that's focused on ISS, they don't go outside of orbital. So that's like really important because if we want infrastructure on the surface, somebody's got to own it, right? So what I'm getting to here is that if another great power decides to go now, we can't catch up. They can go and steamroll it. They can own it if they want to, and Artemis Accords be damned, right? They haven't done that yet, but they could. So I think I think Congress is aware of this stuff. You know, I think that NASA's aware of this stuff, but until the person with the purse strings gets actually scared enough to make some changes, then it's international competition is not really an issue here, or at least not one that we can address.
Awesome. So I don't see any other questions in the Q&A. We have 2 minutes left while we wait for anyone to punch any last minute questions in. I did want to remind everyone that this talk will be uploaded to the AIAA Space Resources Technical Committee YouTube channel, and the slides will be available on AIAA Engage, and a link to those will be available in the video description on YouTube. Um, I'm not seeing any questions pop in, so I guess we'll wrap up for today. But there we go, David. What radius of grid do you see happening?
Fantastic. What I see happening in the beginning is um, uh, up to a kilometer, but it's a question of whether you want to do um, wired or wireless for a small number of assets. I think there's reasons to do one or the other. Um, the the interesting thing is a lot of the envision futures has tens to hundreds of kilometers with gigawatts of power, right? It's a very the long-term vision that NASA has. Get that out of there. Um, Long-term vision that NASA has is very big in infrastructure. But when you look at things like what Artemis is planning, like what the next 10 to 15 years actually holds, it doesn't have to be that far apart and it doesn't have to be that much power. So I envision pragmatism will rule the day when it comes to mission costs in the beginning. From there, once we have infrastructure set up, who knows? Who knows? I would love to see a world where we actually meet some of the Moon to Mars objectives of having a global power grid. That'd be very cool. Um, but until somebody got the money for it, it's probably going to be very small. The important question there is like plume surface interaction, right? So I think that we will land one asset, we will land another asset. That second asset is going to sandblast that first asset, and all of a sudden people are going to be desperately reading Phil Metzger papers to see what we should do about this plume surface interaction thing. And I think if IPEX hasn't flown by then, it very well may be the next thing up because I think that construction robots, multi-purpose construction excavation robots, are going to be really important for berm building right away. You see a lot of these images of like a whole bunch of starships lined up with no berms in between them, right? I think the excavation that's going to happen with every single launch is going to be tremendous. I don't know if y'all saw the first Starship launch, but that thing was excavating the heck out of that concrete, right? So we should, yeah, we should think about the fact that on the moon, where the gravity is 1/6, the particles can actually loop all the way around the moon and hit you in the back with the velocities that they may reach within those plumes. So it's a real issue. I think that we are very likely to run into that problem first, and we're over
Awesome.
time.
Just a little, no problem. So thank you, Hunter. Thank you, everybody. I did put a link to the YouTube channel in the chat. So you should be able to see that. Um, as a reminder, this is the last webinar of the year. We'll be resuming in at the beginning of 2024. So Hunter, thank you for helping close out an awesome year of this webinar series and for a great talk.
Hey, thank you so much for having me. And I appreciate all the questions. It's good to see y'all.
All right, everybody, have a good rest of your year. Talk to you soon.